Okay, we can. So this is the fourth of the series of lectures on sheaves, localizations, and gluing. Tomorrow is one more scheduled, but we will schedule more because we are far from finished. So today I will do some compliments to the first and third lectures, to the lectures on sheaf theory part, not localization part. Of course, there are parallels, and I will later explain common grounds for the two constructions. But today I will first return to the situation of topological spaces and complement with some more constructions there and some details of what I left in the first overview. And then I will do more compliments on the Grothendieck topology side of the story. So first, let's return to usual topological situation. If you remember, we had explained two functors which make between topological spaces over a fixed space. These are just maps of spaces where x tau is a topological space. And the category of, well, maybe category of pre-sheaves, we call it pre-sheaves, but it is also set over the category of open sets and inclusions of tau, of topology tau. So these are open sets and inclusions over open sets, and there is a pair of adjoint functors in between. And from topological spaces over X, you get pre-sheaves of local sections. So that means over every open set, over every object U, you send two sections over U. That's the pre-sheaf, and that can be called gamma. And there is its left adjoint L. I think I was writing pre-sheaves on the left and topological spaces over X on the right in the diagram before. In any case, L is left adjoint of gamma. And so what was this L doing? L was taking a pre-sheaf, and then over X, it constructed a space of all local sections. Sorry, all germs of these sections. So you had in over point X, you will have some space, say Px, and this was a union of this Px. So Px were all sections over X and all germs of section, and these were classes of triples where I had an open set around X. Around X, I have to remember what is X, and I would take some section S where section is section as an element. It's not a section of anything yet at the beginning. Element in P, if P was the starting pre-sheaf, was S was element of P of U. I didn't explicitly, I said that this is an exercise, write down the unit and co-unit of a junction. So the co-unit is always going from left, right, to identity. So you take a topological space over X, call it just E, to E, lambda gamma E to E. So these are this is the pre-sheaf of local sections, and these are germs of it. So any guy here is a germ of something. So any guy here is a class of the form UXXS. Of course, this representative UXS, so this is elements in the total space of this, and I just remind you that the topology upstairs was given as by its basis of topology, and basis of topology was given by images of local sections. And so this UXS is representative of a point there, and then I want to send it to well, you can send it to S of X. That's the thing which you can do, but this looks like it depends very much on it depends on S, but it doesn't, because if in this class you have some other VXT, then this has to be the same not only at X, but in some W, which is open subset of V intersection U. So of course it has the same point, the same as at point X. So this is epsilon. And let's see if I take eta. Eta will go from P to gamma lambda P, gamma LP. So that means this is a map of pre-sheaves. That means that it is pre-sheaves are contravariant functors. So this is a natural transformation. So it has component for every object in this category. So for every U, I have from P of U. So here are sections to gamma L P of U. So that means that you are taking a section. You have to send it somewhere. Well, what will you do? You have to now make a new section, the section not of the original space, but of the space gamma L, of space L of the original space. So that means that you are this is the correct way to write it, that you take germs first, and then you take sections over there which pass through germs. So so around every point X, so this will be some new section S tilde, such that S tilde, when of X, has to be something above X in this stock PX, and stock consists of such guys for various S's, but you take the same S, of course. So it is class of UXS S, where U is simply a domain of original S. Of course, it can be anything smaller. It's the same germ. And with these two guys, you have the usual situation that the triangle identities hold and that you have an injunction. Now we have to say a little bit about maps. This I didn't say anything about this. The maps. And so if you have two in topological spaces over X, of course these are things E prime over X. The maps are, I mentioned that actually, that this is a continuous map from E to E prime, which are over X, so that this triangle commutes. So this is this category, and in the case of pre-sheaves, is of course P to P prime is a natural transformation. However, when you are in this subcategory, which is obtained as, you remember, if I was going from if I would compose this gamma and then lambda, or lambda and then gamma, well, you see, if for pre-sheaves, if you do first L and then gamma, this was called A. This was a sheafification. So the pre-sheaves in this essential image of sheafification functor are pre-sheaves with this gluing property. You remember that if I had a cover U alpha of any U, of any U, open, then sections over U are in one-one correspondence with families of sections over each of those, such that they agree, that their restrictions agree on common intersections. Now, this subcategory was equivalent to the category on this side. You had a category of what we call of local homomorphisms, which called the Tal spaces, and this is exactly this is essential image of L. So this is the same as this pre-sheaves as sheaves. These pre-sheaves which satisfy this condition. Old literature called these guys sheaves. So when we talk about this subcategory, then the claim is that these two descriptions are describe the same guys. If P is isomorphic to gamma of some E, of sections of some E, I mean E over X. This would be E, and then I have some projection, and then I have X, if you want, but we call it just E. So if P is this, then exactly the natural transformations correspond to this. But there is a third description. There is a third description, and this description can be kind of seen from the construction of a pullback. So what is a pullback? So if I have X to Y, a continuous map of topological spaces, and I have E not over X but over Y, then you can define set theoretic pullback E cross Y over X. And in the category of topological spaces, it has a topology so that it is actually the topological pullback. What does it mean? That it's universal object if you take any Z such that the external square is commutative, you have a unique map here. So these are simply pairs EY such that if you take if this is F, that and this is P, then P of E is not Y. Sorry, what am I doing? I'm doing wrong. E cross X over Y. And so P of E is the same as F of X. Well, now this is general construction of a pullback. Now, if you work with étale spaces, then the pullback, the topological pullback, is in fact of étale spaces again étale. So pullback of an étale space, excuse me. Pullback of an étale space is étale. And this will give us third description of maps, only if they are étale spaces. So what this means, look, this guy above every point X has exactly a copy. So so this I will call it F star E. So this space is F star E. So F star E at X is a copy of, you take E, so this is in bijection, so with with E of F of X. So you can take one copy of that. So basically you can take a point in this, in E of F of X, and X comma that. So maybe EY is not the best. Maybe it's better EX. Maybe it was better to have XE than EX. Maybe XE would be better. Maybe X. Well, doesn't matter. So anyway, this here is a union over X of EFX, disjoint union. So you have another copy. If there are more X's which go to the same one, you have many copies of this. And now this has to be topologized. And I will not take, of course, I could take Cartesian product of topological spaces and usual Tikhonov topology, and then just take this is a subspace of this, and then take a subspace topology. But I'm the category of étale spaces, and I claim no, in étale spaces, sections are the images of sections make a base of topology. So every open set is union of images of sections, of local sections. So I have to see now what are the local sections here. If I know what are the local sections, I know what is the topology. But it's described differently. So I can take, you take S from U open, so U open in X, into pullback is continuous. So that means it is a section. It is a local section. If and only if, well, it's the only thing which is kind of logical here or intuitively. Well, you see, this here is this projection to E is a continuous map. So if I have a continuous map from X to here, when I compose with that, this has to be continuous. And nothing else, you know, you have to use just this part of the diagram to construct everything here. If it's true kind of pullback construction. So it's not on, so it's even only if I post compose it so if and only if, how would I call this? Projection to E. Projection to E composed with S is continuous. So this is for the pullback, and you see pullback is now every map from any Z over X. If I have a Z over X to unique to E goes uniquely through this. So now say that this Z is again a tau, so that situation like this, that I have from this to this, but it's not over the same X, it's over the different ones. So new page after. So what I want to have now a situation like this. I have E prime to E. I have here X. I have here Y. So I'm looking at a more general situation than over the same X. And then I will specialize also to the previous situation, but I have a little more ambition here. So you add also this F star E. This is F, which was this was also here, and I had the map here. So here I knew how to describe sections. I explained a little bit ago. So now I can do the same story here. So I can have here a section. So S from X to E prime, a section of any tau space. And so F, and here I will say F tilde. This doesn't, it's not not determined by F, but it's some map which such that the external square is commutative and it's continuous map. So it's continuous map of tau spaces. So of tau spaces, but of tau spaces over different spaces. It is, we say that F tilde is over F. So this kind of maps we want. They're not anymore in the slice category. So S from X to section. And then, of course, it must be that F tilde let's see. So we have F tilde composed S is a section of E. And these sections define of E, and then I this every fiber here and fiber here is isomorphic. I could also go here. I have also section. I also have a section of f star of v. And I say this section is continuous if and only this section is continuous. So, but I'm claiming that f tilde is continuous if for every section S from X to E prime, this F tilde composed with S is continuous. Okay, so for continuous maps, yes, for continuous maps, you can do this. And so really, I check continuous maps from below, from X and Y. I look just in terms of sections, and sections have really to behave well. Okay, this is about the maps, and this F upper star is in fact F upper star makes étale spaces over varying spaces, a fibered category, a fibered category. What this means, you see, well, if I would have various spaces X and Y, remember, and I had over every X, I have all possible étale spaces over Y, and here I have all possible étale spaces over X. And then you can consider these maps, these morphisms of étale spaces over different X and Y. These are simply these commutative squares. So we have one big category of étale spaces. And down there you have topological spaces, which are varying base. And then over every topological space, you have something like this étale spaces over X. It's kind of fiber. It's just part of this étale spaces. And then you can consider spatial morphisms in the étale spaces. So here I have some you have this F upper star to E. This kind of are very special. They are Cartesian in the sense that they have a universal property that if I take any E prime over X and a map over F from E prime to X, then there is a unique map from E prime to F star of V, such that external square commutes. So such a map here is called Cartesian, which satisfies this property, and the composition of these Cartesian maps is Cartesian. And this means that if and above every F such construction exists at least one F star E. There are also isomorphic ones, of course. And so the category which has this structure that above every F there exists such a universal map with this universal property is called the fibered category. Now more constructions which are along these maps. So first of all, if I would have a sheaf or pre-sheaf, if I have a sheaf or a tile space, or a pre-sheaf even, over X or over Y, can I move it between X and Y? And so this pullback is one construction. So this is that I'm pulling it from Y to X, but I can do other way around. I can take construction here. It can be said in terms of the tile spaces. It can be said in terms of pre-sheaves, but we prefer to say it in terms of pre-sheaves because it's easier. So if I have a pre-sheaf P over X, so so what does that mean? So P is from open sets, to oh sorry, from what am I saying? From open sets opposite to category of sets. Then let's see, and this is F. Then we want to have some F lower star P, which will be on open sets on Y. So you want to define what is F lower star of P of U. And you define that this is P of F2 minus 1 U. And the pre-image of an open set is open, and you have no problem. This is well defined, and this is a pre-sheaf. The restrictions are well defined. So this is at the level of pre-sheaves. What if I want to do it with the tile spaces? So well, there is a direct description, but we can simply take a tile space, translate it into pre-sheaf, take its pre-sheaf of sections, do this construction, and then return to a tile spaces by taking germs. This is one description. Another description would be to describe in terms of fibers. So I would take, so I have here some fiber Px. Px is a fiber over some point X. And you want to see what happens in the, so you have to know what is F star P of Fx, F star P of Fx. Am I doing it right? So yes, so I want to know what is F star P at point Fx. So this is some y, and of course you can consider all guys in the okay, so F star P at Y. So you describe in terms of this you define this fiber, and then you look at what is topology, and you use similar tricks. So I will do an exercise. translate above definition to definition in terms of stocks. So stock is, so these are stocks. Okay, so and then it appears that F upper star is a left adjoint of F lower star. So that means that this fibered category here becomes what we call a bifibered category. Bifibered category. It is fibered and it's co-fibered for this guy. And these are left joints, these are right joints. Okay, so every construction, both construction of this and this can be said in both languages of pre-sheaves and étale spaces, but one of them is easier, is more direct in this way, another is more direct in that way. But for F upper star, it is quite instructive to say what is F upper star in terms of pre-sheaves. The construction is so F upper star we explained as in terms of a pullback of topological spaces, what was straightforward. It is the same construction in étale spaces as in topological spaces, and in étale spaces had another description in terms of sections. Topological construction is in terms of sections as well, as I explained above. But let's see why I can't take the same thing like this, but for F. So why wouldn't I say if I have Q was a pre-sheaf over tau topology of Y. So here I write also that it's Y and some topology opposite to set. I can do the same construction with F because, of course, a topological space from open set, if U is open, then F2 minus 1 is again open. But if V is open if V is open in X, then F of V is not open. But you see, everything is constructed in terms of germs on the étale side. So if I want to work on the pre-sheaf side, then you see every point is about something in the neighborhood. So the germ is direct limit construction. I am taking filtered co-limit of things which are nearby. So why wouldn't I do for the whole section that if it consists of points around every point I do something around, and then I'm taking this neighborhood smaller and smaller, why I wouldn't do the same for F of V? So take the family of all U open around, so all neighborhoods. So these are neighborhoods of F of V. And these neighborhoods are smaller and smaller, and I can pass, and then I can take for every of them. So I take F star P of V to be co-limit, direct limit, over all U around which are neighborhoods of F of V. Because F of V can be anything, but around every point you have open sets, so about everything you have a neighborhood. And so I take co-limit over all of this, and I take P of U. So if the map F would be open, then of course there is then V is its own neighborhood, and it's at the end of this filtered system of neighborhoods. So I have all of these, and those are further. So I have you take reverse inclusions because you are taking the co-limit, and the one which is smaller neighborhood of f of v is larger in the sense of this order, and then so it is, I mean, the smaller one is closer to the co-limit that I'm saying. Like for germs, if I have a smaller and smaller neighborhood, they are more and more like a germ. Germ is like just around the point. So what this means, that section here, let's say this in terms of S. What is S? S is again equivalence class of S well, maybe it's not, is S from U to U open. Well, it's not good to say that it goes somewhere, but it's better to say that is in something, because I'm completely in pre-Sheaf language. Is in P of U, P of U, where S is S. So this S is maybe, can say where it is as SU is the same as T, and U is, so U is an F of V, but SU is the same as TU prime if there exists W open, which is around F of V as well, and W is in intersection of U in U prime, and S on W is the same as T on W. So it's the same like germs, but now you do not germ around the point, you do germ around F of V. And this here is an example of a categorical construction, which is called a Kahn extension. It is a Kahn extension. And this here, this filtered system is a Concoma category. And this is, we call it pointwise Kahn extension construction. It is in some sense minimal, minimal or maximal, depending how you call it. It's kind of a minimal approximation of just P of V, but P of V doesn't exist because it's not open. So you want to approximate this construction as closely as possible. You can't construct a P of V. You want to replace this with something what is in some sense best possible, and best possible approximation is this. So in general, Kahn extensions are kind of some sort of closest approximations in some sense of category theory. So this is extremely important. Although we have another construction, we could do it simply as topological spaces, and that was extremely well behaved. But this kind of Kahn extension construction tells you a lot, and tells you it's not the only place where similar reasoning comes in Sheaf theory. It is more than one place where this appears. So I consider that this is very important. So we described, so today, in addition that I explained this epsilon and eta in more detail, I explained a little bit about maps, including maps around different x and y. So now I will switch in the last 15 minutes. I will switch back to Grothendieck topologies. And over there, we were talking about what is Grothendieck topology and what is Sheaf yesterday in the third lecture. So I will now say a little bit about. I will first rephrase this in different terms. Remember, yesterday we had a notion, very important. Well, first we had let's repeat a few things. First, we had a notion of a sieve, as this was J, where C was a category. So this was if C was and C was some sort of an object in C. Then we had some sieve J, sieve on C was some family of arrows into C. So that was such that this family defined a subfunctor of this was a subfunctor of representable functor home S. So this subset of this, but it has the feature that it's a right ideal in some sense. So that meant that if I precompose these arrows which are in J with anything, I will get again arrow in C. And then I had a notion of matching family for a sieve. Matching family for a sieve. And the matching family was that for sieve J. So for every F in J, you looked at the domain of F, and you take for a sieve matching family for a sieve and for a pre-sheaf matching family of sections of elements in the pre-sheaf. So pre-sheaf is P. So for a given pre-sheaf, so you take P at domain of F. So here some D into C or whatever you call it is one of the and you take some X or S. It's like a section. We like to call it S, but you can call it just X. It's an arbitrary element. Everything is now set theoretical. You have some SF, and then P of G if G if the codomain of G is the same as the domain of F, and P of G of SF had to be the same as S on F composed G. This is also in J. So for every guy, it has to be like this. And then I define Grothendieck topology as some family of so a site. I didn't say this word yesterday. But site was a category together with Grothendieck topology. In Grothendieck topology, T was assignment, assigns some family J of C is a family of sieves on C, and then which satisfy some axioms, which I explained yesterday. And we think of sieves, sin j of sieves on C, and we call this covering sieves. These are called covering sieves. And then a sheaf is pre-sheaf such that every matching family for any covering sieve has a unique amalgamation. I didn't use this word yesterday. Yeah, gradually amalgamation. So what was amalgamation? Was so you have a covering sieve J over C, and amalgamation. So I had in each of these domains I have some SF, and amalgamation is S such that P of F of S, that's like a restriction of S on F, is SF. So we have matching family in all of these, and and we want to have one global one on C. For every covering sieve, so for every C and every J in J of C, in capital J of C, you have this property. So amalgamation is this. Now, there are two things which I would like to say. I have less than 10 minutes, so I will probably say just one. So first is I want to express this in terms of exact sequence. And second one, I want to construct, to say that from the pre-sheaves on the site, category we wrote in topology, inside you have category of sheaves. So here I could say simply, I could simply not write tau because pre-sheaf has nothing to do with tau. I can write, but I don't need to write. And there is inclusion. This inclusion has a left adjoint, again left adjoint, which is just like above, which is analog of this A, and this is left adjoint A, and A will be called the sheafification. It's a left adjoint to inclusion. And again, you see, if you have a right adjoint, which is fully faithful, that means that this is a reflective subcategory. That means that the same situation which we had in localization theory. But let's see. And this A of P is constructed by an ingenious construction, but not, it's quite simple exactly, but it has to be done very precisely. It's called a plus construction. I think I will not make it today because I have too little time, but just several minutes. But there is, if I repeat this plus construction twice, there is a construction, and this construction twice, it makes actually sense because you also have, you can consider like in the case of sheaves on topological spaces, we had this separated pre-sheaf, so that if there is amalgamation that it's unique. That's we call it separated pre-sheaf or a mono pre-sheaf. So in first phase, you get into mono pre-sheaves. And then in the second phase for mono pre-sheaves, if you have a pre-sheaf, then A of P is only once plus construction. So you are kind of making pre-sheaf better. In first you make it into mono pre-sheaf, and then if you make it mono pre-sheaf, then automatically plus construction will be. And plus construction is in terms of matching families. But I will first say the sheaf condition as an exact sequence, because this takes less time, and then this will take a little bit more time. So I will do it as a first thing tomorrow, and then I will do more things. And tomorrow's lecture, I would like, if there is no lecture after my lecture, I would like it to be longer, not exactly as it's scheduled to 11:05, but it will be a little longer if there is no lecture after that. I will take some freedom to make it longer, and then we will schedule more lectures for later, probably next week. I think I will need several more lectures. We'll see how much time we can put, but please watch at the updates of the schedule, and I will schedule more lectures. Okay, so let's write down the condition, the sheaf condition as an equalizer sequence, or as an equalizer sequence. So we take, so for every J a covering sieve, we had the following. We have P of domain of F, and you take, so where the matching family lives. Well, it's a family of SFs, where F is in little j. And it's matching family if it satisfies some condition. So I will take now P of domain of F, and this family will be then in the product of this over all F in J. But now, to say that it's a family, it's a matching family, you have to compare for all G. So take all G such that the codomain of G equals domain of F. We had the condition. What was the condition? P of G of F was S G F. Okay, S of G composed with F, S G F. So you can take now all such ones. So so take all G's such that, so all G's such that codomain G is domain F. So they will index, I can consider all this as G composed Fs, all such guys. And so they live in the product of domains of G, this S of G composed with F, and this guy. So these both live here. Domain G, where, as I said, codomain G is domain F, and F is in J. And now I have two maps. One is that you simply take P of G of your, here's a mistyped, it is SF. P of G of S, P of G of SF. So here you have some SF, you simply do it P of G of that. And I get from here to here. This is assigning to this matching family. Well, this is on G. Of course, this is a product of all such guys. It's a tuple in this product. So for every G, you have a P of G of that guy. But what you can also do, if you have a family of these guys, you can simply send it at every of these guys. You simply take this as G composed with F, because this is, again, you can read it from here. There is a map, because this is S F's in J, and S composed J S of G comma F is also in J, but some of them appear more than once, possibly. Because you can, for example, you can be G composed with some F, but it can be directly as identity composed with itself, etc. So these some of them appear in more than one way. That's what I wanted to say. So this is a tautological, how to say, simply choose this S. So there is another map. How would I call it? I call it simply canonical, because it just chooses this this S from here. You have to look at. You don't care which is F. You don't care where it's coming from. You just care. You just take as if it would be here. F is this domain. G is the same as domain of G composed of G composed F. No, something is wrong. Domain of F composed G, of F composed with G. Okay. So the left hand side comes from above. The lower side comes from below. From right hand side is below. So simply don't care here about anything. You just can read here the whole family, and this domain of G, or domain F composed with G, it can be read here, because this composition is also in J. This is in J, so it can be read here. I can find that S of this guy. I can find it in this family. So from this, I can read it here. So I have a map. And now I'm saying that this defines a unique element in P of C, where C is where covering C is over C. That would be, if you want, this is a codomain. This is a codomain of all these F's in J. And this sequence is exact in the sense that, and what is this map? This map, of course, sends S to P of G of P of F of P of F of S, where F is in J. This tuple in the product. So so we want to say that if you take that this is equalizer sequence, so that means that image of for image of Fs, these two guys agree that there is such an S, there is unique such an S, such that they agree. So I'm just expressing this in terms of exact sequence. Now There was exact sequence which I didn't write, but it's well known for topological spaces. It's much simpler. For topological spaces, if you have a U alpha is the cover of U, and you have a pre-sheaf on U, then you have simply restrictions. So you have P of U alpha, and then you simply S goes to restrictions, to the family of restriction S restricted to U alpha, and product over U over all alpha tuple over all alpha in the cover, all alpha in the cover, and then you take product of U alpha intersection U beta. And on one side, you will have restrictions from U alpha to U alpha intersection U beta, and on another you have U beta, P of U beta to P of U alpha intersection U beta. So they induce maps, and these maps have to agree. So here's all pairs alpha, alpha, beta. So in intersection of U alpha intersection U beta for pair alpha beta, in one case you are taking restriction from U alpha, in another case you take restriction of U beta. And this is an exact sequence. This is just a Sheaf condition. So this is the Sheaf condition. This is the Sheaf condition for usual sheaves, and this is for Grothendieck topology. And then there is a notion of Grothendieck pre-topology. I will say more tomorrow, or a basis for Grothendieck topology. So this will be family. This will be families which are called also covering families of an object. So you have, if you have an object C, so again you have a category, and you will have now pre-topology. So pre-topology is, so the smallest sieve which is generated by pre-topology will be built with topology. This is made that way. So we have some families of arrows into C you call covering families. They are not C. It's not a sieve, but it generates some sort of minimal sieve. So it is some sort of a basis of topology, and it satisfies again three axioms like yesterday. But one is that say identity is in, but usually you work with pre-topologies in categories with pullbacks. So the other two axioms can be said in terms of pullbacks, namely if I have a family over C, so I have some C alphas and F alphas, and you have any D to this, then you can do pullbacks. You can do D cross C alpha over C. And then you will also have conditions. What happens with this covering family when you do the pullbacks? And then you can make again condition what is sheaf, and this condition is usually expressed in terms of exact sequence. But exact sequence is just like this one here. The only thing is you don't have intersection, but instead of intersection here you will have C alpha cross C beta over C. You will have P on a pullback, and the maps are very easily defined. So this I will say more details maybe tomorrow. And so any kind of Sheaf condition is usually some sort of equalizer condition, but because of different setups, you need some some different constructions to express how you really work with analogs of sections. Analogs of these local sections are a little bit differently behaving in formalism, but it's essentially the same thing. And then the localization, the situation of localization. You remember I had a ring. I mean, just the localization category. I mean, there are various kinds of localizations, but if you consider the localization of as a localization functors on the categories of modules, that can be also expressed in terms of analog of Grothendieck topology. It can be said like this one. The only thing is that all these guys have the values in abelian groups. And this is, so one works with some sort of submodules, and really these sheaves will be sheaves in the sense of pre-additive categories. So they will be also some sort of additive version of sieve. So as I said, sieve is a multi-object version of a right ideal. So you have a right ideal not only in a ring but in a ringoid. Ringoid is a small pre-additive category, and again the same kind of condition holds. And then one more thing in this situation, in this story, is that if you look at the category of this category of pre-sheaves, and you could consider inside this category of sheaves, then for these sheaves, some things are better behaved than for pre-sheaves, and some limit kind of constructions. And there is a viewpoint on sheaves that you are basically, by any category X, you can embed into the category of pre-sheaves by the pre-sheaves, well, it's not good to write X, but write C into pre-sheaves on C. This is just C from C opposite to sets category by Yoneda embedding. And this category is much behaved than the usual category C. You see, some arbitrary category can be badly behaved, some geometrical category, but you embed it here. Here you have much more constructions. But some kind of limit kind of constructions or co-limit constructions, you have everything here. But does this embedding preserves everything? So behavior with respect to limits and co-limits is different. But then if you want some more construction that behaves well with respect to just to some limits which are constructed in terms of covers, then you can make this category also better, such that the composition, such that not composition, but that you can factor. You don't go into pre-sheaves, but you go here in a smaller category, and then this functor is somewhat better behaved with respect to covers. That's a point of view. And then I can take not Grothendieck topology covers, but I can take some other kind of constructions, some other kind of cones, which are not related to Grothendieck topologies, and construct again candidate of this kind of sheaf-like construction. And one of such construction is due Rosenberg, but there are also some other authors which have variants of this, which is certain generalization of sheaf theory, which simply takes pre-sheaves with some properties with respect to some cone-like constructions, not Grothendieck, not covers, but some other constructions, to make this embedding, this Yoneda embedding, a little bit better. And this is kind of general mathematical viewpoint why we do sheaf theory, because we want to make a better category category which behaves well with respect to covers. Covers are kind of refinements of a object into some smaller object and making these pieces, and these pieces kind of piece together, but in the same time I have bigger category in which I have more constructions. In C you can maybe not make fibered products, or some constructions are not possible. Here you have more freedom, but you are losing something, and sheaves happen to make it better. That's one of the reasons. Another reason is that with sheaves, if sheaves are with values in abelian groups or something like that, you can make cohomology theories. So that's kind of geometric thing. And also sometimes you want to objects to glue objects in C itself. So maybe there is some subcategory of these sheaves which are really locally looking like objects in C. These are, we call locally affine objects, which have local models in C. And then we make some sort of like a manifold-like objects where a local picture is like a C. And that's another. So these are not like sheaves, generalization of sheaves over a space, but you consider space itself as some sort of a sheaf, and then you glue these spaces into more general sheaves. So, for example, manifolds are more general than open sets in Rn. Schemes are more general than affine schemes. And you can do this also by sheaf construction. So I want to end this course next week sometime, or maybe the week after that. I don't know how many lectures I will give more, by having this general picture that sheaves are really useful in many ways. They make situation better. They feel the situation downstairs, and they feel also the gluing. But for gluing, I need also to have a little more general situation. I need to say what gluing is, not only how to piece together sections, but how to piece together objects. And this would be the subject of descent theory. For descent theory, I will need this kind of construction. These fibered categories are used for this. So I will give a small sketch in one of the lectures also of fibered categories and how they can be used over Grothendieck topologies or over topological spaces to do more general gluing. That's all for today. It was a little longer, but today I think I will be certainly half an hour longer to say what I want to say tomorrow. Okay, thank you very much. I stop sharing and I stop recording.